Hello, welcome to Richardson RFPD's Tech Chat. I'm Kirk Barton, Field Application Engineer for Richardson RFPD, and I'm here today with Ryan Schnell, Product Application Engineer for Analog Devices, Inc. Thanks for joining Tech Chat today, Ryan.
Thanks, Kirk.
Today we're going to be discussing SiC and GaN drive voltages, unipolar and bipolar. So looking at the various technologies, Ryan, whether it's silicon carbide or wide bandgap semis like GaN and SiC, their different gate drive voltage levels are required for optimal performance. Can you highlight a few of the examples of the different levels required for the different technologies?
Definitely. So, as you mentioned, there's different voltage levels required by each different switch technology. I like to split them into two different sets, a unipolar and a bipolar. And what we usually mean by that is unipolar is going from 0 volts to some specific gate voltage, and bipolar goes negative. And the reason for going negative is to create a stronger off, and that can prevent against Miller injection as well as keep your switches very off. For regular silicon, we usually see drives from 0 to 15 or a unipolar signal. With silicon IGBTs, we usually go bipolar, sometimes going negative 15 all the way to 15. Silicon carbide and GaN can be bipolar, or a GaN MOSFET in a cascode connection basically has you interfacing with a regular silicon MOSFET, so it's unipolar.
Okay, good, thank you. Now, gate drive configuration is going to vary depending on whether it's bipolar or unipolar. Can you give some examples of how the isolated supplies that are used in these gate drive applications are configured in both the bipolar and unipolar applications?
Yeah. So there are natively unipolar and natively bipolar gate drives. One example for a unipolar would be the ADUM4120. On its secondary side, you only see a VDD 2 pin and a ground 2 pin. You basically can only have a 0 to X voltage drive out of it. The ADUM4135 is an example of a natively bipolar system having 3 power pins, a VDD2, a ground 2, and a VSS2 pin, allowing you to put the positive and negative voltages into the system.
Okay. And it looks like, I mean, based on if you're using 2 separate supplies, you could total up quite a few isolated power supplies if you have multiple devices in parallel or something, right?
Yeah, so one regular configuration that we come into a lot is a half bridge. And if we're doing a 3-phase system with 3 different half bridges, every single high side needs its own isolated supply. And if you're requiring bipolar drive, that doubles the amount necessary. And so for a system like on the right, we get a lot of drives out of it, a lot of isolated supplies necessary.
Yeah, okay. Now, are there easier ways to implement a bipolar drive level from, say, like a single unipolar device?
Yeah, let me try to kill 2 birds with 1 stone here. And we're going to use the ADUM4120, which you remember is natively unipolar. And right now we only have 1 isolated supply. But if we're wanting to turn it into a bipolar drive, we can offset it from what the power device is by using 2 separate isolated supplies, much like earlier.
Okay.
In this example, the capacitor 1 or C1 carries the positive voltage, and C2 carries the negative voltage. In this way, we can create a bipolar action from a unipolar system.
Okay. And those can be 2 separate supplies or maybe an integrated bipolar solution?
Yeah, Recom has some really nice dual output solutions that are in the regular drives for IGBTs and silicon carbide.
Okay, good. Now, what about the option of a more simplified approach? Because I know some of those isolated bipolar supplies can be a little pricey, especially if you're using multiple in a design. Is there an easier way to implement this?
Yeah, if you find yourself having only a single isolated supply on the secondary side, but you still need bipolar drive. One neat trick is to use a Zener diode. And by either putting a Zener diode system with a Zener at the top or at the bottom, you can create that offset voltage. And just like before, C1 carries the positive voltage and C2 carries the negative voltage. But in these examples, we really only need one isolated power supply per system. Whichever leg you put the Zener diode on first is going to be the one that powers up before the other side and give you better regulation for that side.
Okay. Now, so is there any particular benefit to, you know, what's in that series Zener regulator circuit, whether the Zener diode is in the top position or the lower position?
Yeah.
Any benefit to that?
So putting it in the top will have your positive rail more closely regulated. And if you put it in the bottom, you'll have a more closely regulated negative drive. Most people want the positive drive to be more accurate.
Okay, okay. And it's probably, I mean, like a silicon carbide gate drive level of +15, -4, depending on how much tolerance there is in those gate drive levels, you'll probably, the tighter tolerance one, you'd want the Zener regulator on.
Yep, exactly.
Okay, okay. Any particular concerns when selecting the specific Zener diode used?
You usually want the lowest quiescent current in order to have lower losses. Another concern that comes up while using Zener diodes is if we're using a system, a natively unipolar system like the 4120 in this example, the UVLO for the 4120 is referenced to ground 2, which is the negative rail of the system.
Okay.
So you'll have to choose a slightly higher UVLO compared to a unipolar case.
Okay, okay. And with that isolated supply that you choose, it just has to be able to supply the Zener regulator current as well as the maximum gate drive current required to turn off and on the device.
Exactly.
Okay.
And the isolated power supply that you choose for this example would be 9 volts because we're spanning the whole +5 and -4 volts in this system.
Okay, yeah, right, right. Okay, very good, very good. Anything else of particular interest, Ryan?
I think that about covers it.
Okay, well, thank you for going over the details. We appreciate your time today, and thank you all for watching our Tech Chat video. You can learn more about this and other topics on the Richardson RFPD GaN and SiC Tech Hub. Follow our Ask an Expert link to submit questions relative to design challenges you may have. Thanks again, Ryan.
Thank you.